Hi, everybody. All right, so at this point, we have finished talking about the metabolism of glucose in the body, how glucose is used in order to get energy in the form of ATP. Okay, so remember when we first started talking about glycolysis, and we were talking about how much glucose or how many ATPs a glucose molecule can make, I mentioned that although glucose is a great fast source of cellular energy, the really exergonic source of energy and the main source of energy in especially humans is actually from fatty acids. So today we're going to talk about Chapter 20, which is fatty acid metabolism. I'm dividing this into two parts. So this is part 1, where we're talking focused more on catabolism in sections 1, 2, and 3 of your textbook. So as always, here are your learning objectives. Make sure we can define and use key terms. We'll describe the digestion of triglycerides and how they are transported from your digestive system to various tissues for either storage or energy production. We will compare and contrast various lipoproteins, describe beta oxidation for even-numbered fatty acids, odd-numbered fatty acids, as well as unsaturated fatty acids. We'll calculate the number of ATPs produced from a given fatty acid, and then we'll describe ketone bodies, where they come from, and what they are used for. Okay, so digestion and transport. So triglycerides constitute about 90% of the dietary lipids, and they are the major form of metabolic energy storage. So if you want to kind of have a review on fatty acids and triglycerides, especially with nomenclature, how they are named, because that might be important come exam time, you need to be able to review Chapter 9. Okay, so triglycerides are digested in the small intestine by pancreatic lipase. So pancreatic lipase will remove, so if you remember we have the glycerol unit with 3 acyl chains, so we have acyl chain 1, 2, and 3. Lipase will actually sequentially remove acyl chain 1, followed by acyl chain 2, I do believe, in that order. So we will have a mixture upon initial digestion of unlipated triglycerides. We'll have diglycerides, monoglycerides, and then just fatty acid chains. Bile salts. Now remember, triglycerides are fats, so they are mostly hydrophobic, so they are insoluble in water solutions. So bile salts are used to help solubilize triglycerides, so they're sort of soapy materials in order to increase the digestion as well as the absorption of fats into the bloodstream. So bile salts are amphipathic, remember, so they're both hydrophilic and hydrophobic. Okay. Cholesterol derivatives, they are synthesized by the liver. After synthesis in the liver, they are stored in the gallbladder until they are excreted into the small intestines to help digest lipids. So people who have bile duct clogs, okay, so there's certain disorders that can cause that. They are unable to absorb or fully digest their triglycerides, and so they won't get good absorption of fat in their diet. And so remember, we do need fat, and so they usually have very poor nutrition. They're very weak and can even possibly get very sick and die from this. There's actually, if you look up cystic fibrosis, one of the problems in cystic fibrosis is the sodium gated channels in the cell membranes are deformed, and in order for bile salts to be excreted, it's usually coupled with these sodium gated channels. So if the sodium gated channels are no longer working, then the excretion of the bile salts no longer happen, and now And also excretion of lipases from the pancreas can't happen as well. So these patients with cystic fibrosis are unable to absorb their dietary fat. Alrighty. So the partially digested fatty acids, mono and diacylglycerides, are absorbed through the cell lining of the small intestines, remember also with the help of bile salts. The lipids are then transported through the body as lipoproteins. So we have 5 different types of lipoproteins, and they usually vary based on their density. Okay, so lower density lipoproteins have more triglyceride and less cholesterol, where high density have lower TG and increased cholesterol. And the density is literally what it is. It's a measure of these molecules' density, okay? So their molecular weight per volume. So as we go to higher density, we become smaller and more compact, and thus have a higher density. All right? So chylomicrons, they transport dietary fatty acids to muscle and adipose tissue, as well as dietary cholesterol to the liver. Okay, so from the digestive tract to the muscle tissue, these will transport those fatty acids that we just digested to other tissues in the body. And then on their way back, they'll transport the dietary cholesterol to the liver. Very low density lipoproteins will transport endogenous triglycerides and cholesterol. So these are fats that are synthesized by the body. So yes, some fats we take in through diet, but there are some fats we need that we don't get through our diet all the time, and so we synthesize them ourselves. LDL, so this is intermediate density and low density. These are created after the very low density lipoproteins loses some triglycerides, so they begin to increase in density. LDLs can be taken up through endocytosis into cells needing cholesterol. This is through LDL receptors. So remember, a lot of you were talking about drugs that are used to block LDL receptors for patients with high cholesterol. And then HDL, high-density lipoproteins, remove cholesterol from tissues and transports them to the liver. And the liver is the only organ capable of disposing of significant quantities of cholesterol. So HDL is very important. So your parents, you may have listened to them after they come home from their doctor and get their blood profile, their blood lipid profile. When they're getting their blood lipid profile, what they are measuring are their levels of LDL to HDL. Okay, so you want high HDL and low LDL, right? So if you have high HDL, because if you have high cholesterol, your HDL is able to remove that cholesterol and take it to your liver. And you want to decrease your LDL because that's what's going to deliver cholesterol to the cells. And if you already have enough cholesterol, you don't want that to happen. So if we look, table 20.1 kind of summarizes our characteristics of these lipoproteins. As you can see, we can see how our density increases as we go from very low density and chylomicrons over to the high density lipoproteins. We also see our particle diameter. Again, as we decrease in diameter, we will increase in density. And then our particle masses. We can see our percentages of protein. The high density lipoproteins have much more high density than, say, the chylomicrons. We can look at our phospholipid percentages, our free cholesterol percentages. See, our LDL has a lot of free cholesterol. Triacylglyceride concentrations, as well as cholesterol ester concentrations. Okay, the major Apolipoproteins, these are the proteins that are used to help pack these lipids into these lipoprotein vessels in order to transport them to and from the body. Here we can kind of see how these lipoproteins interact in the body. So we can see HDL is taking cholesterol from cells to the liver. LDL is taking cholesterol and transporting it into cells. IDL, VLDL, the cholesterol-rich chylomicron remnants. So these are chylomicrons that have already transported their glycerides and their triglycerides and fatty acids to tissues, and they're now taking cholesterol back into the liver, which then gets transported by VLDL back into the blood. As more fat is used up in these, it becomes IDL. IDL can then become LDL. LDL goes and deposits their cholesterol into the cells. HDL can take that cholesterol back up and then bring it back to the liver. So now that we talked about how these fats are initially digested and primed and then either taken to the tissue for storage or taken to tissues for direct oxidation, we're now going to talk about how we further metabolize these fatty acids through fatty acid oxidation. So the first thing we need to do is we need to prepare these fatty acids to acylate or to activate them with CoA. All right, so triacylglycerides are stored in adipocytes and are released for oxidative catabolism by hormone-sensitive lipase. So we have another lipase here that's going to cleave one of the acyl chains off of these triglycerides, monoglycerides, or diglycerides when energy is needed. So to ready fatty acid for oxidation, they are first activated by acyl-CoA synthesis. All right, so these are located in the ER, endoplasmic reticulum, or the outer mitochondrial membrane. So this is going to be more in the cytosol area, okay? Fatty acid, so here's our reaction. We have a fatty acid that's been cleaved from a triacylglyceride by a lipase. We have a coenzyme A, and we have to use an ATP in order to add that coenzyme A to our acyl chain, and then we're going to get AMP plus PPI. So if you remember, the energy released when we cleave both phosphate groups from an AMP is about 30 kilojoules per mole, and then this PPI is going to spontaneously break apart for I believe we'll look it up in the book, but I believe it's 60 kilojoules per mole. So we're going to get a total of 90 kilojoules per mole. This is a very exergonic process because acylating or putting this CoA on this acyl chain requires a lot of energy. And again, remember this reaction is governed by acyl-CoA synthesis. Okay? So once activated in the cytosol, acyl-CoAs are brought into the mitochondria with carnitine, and this is how we explain this. So here we have our cytosol, here we have our matrix. So our activated acyl chain with CoA on it, the acyl chain is transferred using carnitine palmitoyltransferase onto a carnitine molecule. That carnitine molecule that is now acylated is transported into the mitochondria using carnitine carrier protein. Once it's in the mitochondria, there is carnitine palmitoyltransferase 2. All right, so, or we just, palmitoyl makes it specific for palmitic acid, so if we want to be more generic, we can just say carnitine transferase 2. Carnitine transferase 2 then removes the acyl chain and transfers it to another CoA molecule, and then carnitine is transported back into the cytosol, and we're left with now our coenzyme A acyl activated acyl group to continue our oxidation inside the matrix. Alright, so beta oxidation is then used to degrade fatty acids into acetyl-CoA. So if you remember, acetyl-CoAs are one of those metabolites that's used early on in the citric acid cycle. All right, so acyl-CoA dehydrogenase. So this is done in 4 steps, as you can see here. So in step 1, we use a dehydrogenase to create a trans alpha-beta double bond using FAD. All right, so we are going to oxidize or reduce FAD in order to create this trans double bond in the acyl-CoA that we just transported into the mitochondria. In step 2, we hydrate the double bond using enyl-CoA hydratase. In step 3, we have 3L hydroxyl-CoA dehydrogenase, or also called HAD, uses NAD+ to oxidize and form a beta ketoacyl-CoA. In step 4, we cleave between the alpha carbon and the beta carbon, which is catalyzed by beta ketoacyl-CoA thiolase to form an acetyl-CoA and a new acyl-CoA chain that has 2 less carbons on it. So let's look at that in a little more detail, okay? So here we have step 1. We have our acyl chain, and so we can see our alpha and our beta carbon adjacent to the coenzyme A. Acyl-CoA dehydrogenase uses FAD to dehydrate and, or not dehydrate, but to oxidize the acyl-CoA in order to form a double bond. And so see, now we have a reduced FADH2 that can then go through the electron transport chain and produce ATP. Now our unsaturated trans, so this is very important, creates a trans double bond. So our unsaturated acyl-CoA with a trans double bond is then hydrated using enyl-CoA hydratase here. Now hydroxyacyl-CoA is then oxidized using hydroxyacyl-CoA dehydrogenase and NAD+. So we're going to reduce NAD+ to make NADH. Again, this can go through the electron transport chain to produce ATP. And now we have a ketoacyl. So we have a beta, right? So there's our alpha, here's our beta. We have a beta ketoacyl-CoA, which is a substrate for beta ketoacyl-CoA thiolase. So by adding another coenzyme A, with this enzyme, we're going to cleave at the alpha and beta in order to make fatty acyl-CoA and an acetyl-CoA. All right, so this fatty acid-CoA is 2 carbon atoms shorter than what we started with here. All right, so if we started with a 16 long, so palmitoyl acid, we would end up with a 14 long carbon acyl chain. All right, and now we also have acetyl-CoA, which acetyl-CoA can then go into the citric acid cycle to then produce more ATP. All right, so now we have the question of how do we oxidize unsaturated fatty acids? So let's say we have this fatty acid here, right? So we have a double bond between this carbon and this carbon. So you did see, if we look back, if it was a trans double bond, it wouldn't be an issue, right? Because that's actually the product of step 1. However, most unsaturated fatty acids contain cis double bonds. Remember, you can go back to chapter 9 to talk about why we would use cis double bonds versus trans double bonds in nature. But these are not substrates of HAD in step 3 of beta oxidation. So in order to overcome that, we utilize isomerases to convert the cis to the trans isomer, and reductases are used when double bonds come into conjugation. So in most fatty acids, our double bonds are not in conjugation. But remember, as we're going through beta oxidation, we're going to cleave every 2. And eventually, these double bonds could come into conjugation between step 1 and step 2 when we form a double bond in our preliminary beta oxidation. So let's look at that in a little more detail. So here's problem 1. All right, we have a beta carbon, so beta to the CoA is in a double bond. And remember, it's a cis double bond. So all we have to do then is we use an isomerase to isomerize that cis into a trans. Once we do that, then we can go through a round of beta oxidation. All right, so the problem comes in now is after we go through this round of beta oxidation, this double bond, right, now moves up to where it is in conjugation with the double bond formed in this step, okay? When that happens, we have to use another enzyme, dienyl-CoA reductase, in order to to reduce this double bond. And then so we reduce the double bond formed here in the beta oxidation step, and then we are left with this double bond between carbons 3 and carbons 4. Okay? And then we just isomerize so that that double bond is moved between carbons 3 and carbons 2. Okay? So now it's just as if we're here at this step where we have that double bond between the alpha and the beta, or we have that beta trans. This would be our alpha, okay? No, that's right. This one's alpha, this one's beta, okay? So we have, just like we did in the product after step 1 of beta oxidation. All right, and then we can continue beta oxidation. Another problem exists. So problem 3 is when we have our trans double bond between 3 and 2, and we have another double bond that we're in conjugation with. So it's like we're here, but we've got another double bond here that is cis. So then we use an isomerase to make the double bond between 5 and 4 trans, a reductase to eliminate one of those double bonds, and then an isomerase to, again, move the double bond back between 3 and 2 instead of 3 and 4. All right? Now, what happens when we have odd-chain fatty acids? So remember, when we're doing beta oxidation, we're losing 2 carbons each round of beta oxidation on an acyl chain. So what happens if we have a 17-carbon long fatty acid? You're going to end up, at the last round of beta oxidation, you'll have an acetyl-CoA, right, which is 2 carbons long. And then we're going to have a 3-carbon long CoA called propenyl-CoA. So this can actually be utilized by the body, by the mitochondria, in order to make succinyl-CoA. Okay, so it's converted to succinyl-CoA in 3 steps. So step 1, we have a carboxylase that uses ATP and CO2 to make methylmalonyl-CoA. Then we have a methylamyl-CoA racemase to do an isomerization reaction. And then methylamyl-CoA is then mutated in order to make succinyl-CoA. All right. So succinyl-CoA then can be used directly, well, a little indirectly, but it is used in the citric acid cycle. All right. So the oxidation of fatty acids is highly exergonic. So if we think about this, if you go back, remember each round of beta oxidation produces 1 NADH, 1 FADH, 2, and 1 acetyl-CoA. So let's go back and look at where those come from. And this is a little messy. Let's erase this page. Okay, so if you look between step 1 and step 2, or at step 1, this is where we make our FADH2. In step 3, we make our NADH. And then at the end of the first round of beta oxidation, we have our acetyl-CoA. But remember, we would have multiple rounds for one acyl chain. If we had a 16 long, so it's palmitoyl fatty acid, we're able to do 8 rounds of beta oxidation. So that's going to give us 8 NADHs, 8 FADHs, and 8 acetyl-CoAs. Now, each of these acetyl-CoAs can go into the citric acid cycle, right? And then we're going to make a number of FADH2s and a number of NADH2s. So let's come back. All right. So if we're looking at palmitoyl-CoA, all right, let me get my textbook real quick so that we can work out this calculation together. So if we're looking at palmitoyl-CoA, palmitoyl is a 16 long, right? So we're going to go through 8 rounds of beta oxidation, which that's going to create 8 NADHs, 8 FADH2s, and 8 acetyl-CoAs. Now, each acetyl-CoA, right, can produce, let's see, oh wait, is palmitoyl, no, that's right, okay. So in the citric acid cycle, if we go back, we can remember that the citric acid cycle, for every acetyl-CoA, we are going to produce 1, 2, 3 NADs. So that's going to be 8 times 3 NADH plus 1 FADH2. So 8 times 1 FADH2. All right, so that's coming from these 8 acetyl-CoAs. All right, so we got 8 times 3, which is 24 NADHs and 8 FADH2s to add to our additional 8 NADHs. So we're going to have, so if we add these in, right, then we are going to have 32 NADHs, 16 FADH2s, okay? Now remember, each round in the citric acid cycle, we also produce a GTP, which can then be converted to ATP. So that's an additional 8 ATP that's produced per acetyl-CoA. And now remember, if for every NADH in the electron transport chain can drive the oxidation for oxidative phosphorylation of, where did it go? Where's the control? I think it's 2.7, but I just want to make sure before. Yes, here we go, 2.5. All right, so every NADH can make 2.5 ATP, and every FADH2 can generate about 1.5 ATP. Okay? So based on that, I'm going to let you finish that math out on your own in order to calculate how many ATP a 16O fatty acid chain can produce through beta oxidation. All right, and then you can compare that to every ATP that a molecule of glucose can produce. All right? So now we're going to finish up this lecture and talking about ketone bodies. So acetyl-CoA, when it's released during beta oxidation in most tissues, is going to be used in order to go through the citric acid cycle. However, in the liver, a significant amount of acetyl-CoA is converted to acetoacetate or to hydroxybutyrate. These compounds, along with acetone, are all called ketone bodies collectively. So these are important metabolic fuels for peripheral tissues, such as the heart and skeletal muscle, and under starvation conditions, the brains will use ketone bodies as well. So ketosis is a condition in which acetoacetate is produced faster than it is metabolized. This is often seen in diabetic patients, and it's often characterized by having sweet-smelling breath because of the rich acetone environment. All right, so let's take a look at how these ketone bodies are formed. So you get two acetyl-CoA groups come together using a thiolase to make acetyl-acyl-CoA. The hydroxymethyl-glutarate-CoA synthase, or HMG-CoA synthase, then produces the beta-hydroxy beta-methyl-glutarate-CoA, or HMG-CoA. All right, so we get another methyl-CoA comes in and is added to the end of our acetyl-CoA. Then a lyse, so HMG-CoA lyse, then breaks off an acetyl-CoA group, and we have our acetoacetate. Acetoacetate can then be converted using a dehydrogenase. So we're going to oxidize NADH to make NAD+, and we're going to transfer those electrons over to hydroxybutyrate. All right, and then so now that we have hydroxybutyrate, we still have an acetyl-CoA that can undergo the citric acid cycle, and we may have some acetoacetate. Hydroxybutyrate can then be transferred from the liver to peripheral tissue and then utilized for energy, for quick energy catabolism, right? So hydroxybutyrate is oxidized using a dehydrogenase to generate NADH, leaving us with acetoacetate. Acetoacetate is then combined with succinyl-CoA with a 3-ketoacyl-CoA transferase. So we end up with succinate. Again, that can go through the citric acid cycle. This can go through the electron transport chain. The acetyl-acetyl-CoA, right? So we transferred the CoA from succinyl-CoA over to acetoacetate. So acetoacetyl-CoA is then cleaved by thiolase, and another CoA group is brought into this reaction in order to make two acetyl-CoAs that can go through the citric acid cycle as well. Okay? All right, so this is the end of the lecture for today. So I'm going to ask you guys for a quick favor. Let's go to this page because it's sort of clean. So for those of you who made it through this whole lecture today and actually watched this lecture, I'm just kind of trying to do a little experiment to see are people actually engaging in these video lectures and watching them before class. So if you could, in the next class meeting, I'm going to come in purposely about 5 minutes late to kind of give everybody time. go up to the chalkboard in the front, okay, of the room. Let's get to play here. All right, go to the chalkboard in the front of the room and just start a tally. All right, and so as you come in, add a tally if you actually watch this video. If a student who doesn't know what you're doing asks you what you're doing, just sort of kind of shrug it off and be like, don't worry about it. All right, and so this way, when I come in, I'm going to come in to class about 5 minutes late. So this way, I don't see who has or hasn't watched the video, so it's sort of left a little anonymous, but I can kind of get an idea of who is actually engaging in those videos prior to class, and it can give me an idea of some things that I may need to change or incentivize in order to increase that participation, unless, I get up there and I see 20 tallies, and I'll be thrilled. Okay? So you guys have a great day, and I will see you in class. Oh, come here.